How's it going this morning? What are we working on? Oh boy. Just in case you missed it the first time. Oh, should log in. I know on Friday there were like a couple of people working on looking at the pendulum, like how to set up, like what is the pendulum equation, and just running
on the pendulum equation.
Yeah.
Is it supposed to be sine or cosine?
It definitely sine.
Okay.
I mean you.
It's just the angles don't make sense with cosine.
Yeah, because then negative cosine.
Because then it's going between angles of like 5 degrees and negative 200 degrees. It's like it's swinging on one side.
Yeah, it'll swing. What does it end up being? Let me see. Oh yeah, we're timing it. Yeah, 5 because if you put in cosine, then 90, is it 90 degrees? Negative 90 is the like equilibrium angle. So if you're 60 degrees, now it's going to swing to up and around. Yeah, so it should be sine of theta. And I think I had fixed it in mine, but for some reason it didn't update the your tool set in here. The solution is theta 0 cosine omega t, like root t, where omega is root t over L t. What I wanted to do was so once you know that like the equation of motion for pendulum is that acceleration is that negative g over L sine theta, then our derivatives, defining those, again, just two first order derivatives. So taking one second order equation, now it's two first order. So my input is always going to be the state, and here my state is both the angle and how fast it's moving, how fast it's changing. So then derivatives of those two inputs are going to be d theta, which is one of my state variables anyway, but it's also the definition of d theta dt. And then my actual like equation of motion, which is defining that negative g over L times sine theta. And we can check that this is kind of working. Like if you have a pendulum and you bring it up to 90 degrees, it should free fall for like a fraction of an angle. Like as soon as the angle starts increasing, then it'll have some drop in that angular acceleration. At least for this one, because it has L is 1 meter. So, and if I'm down at 0, I should have 0 acceleration because I'm right at the equilibrium point. So it seems like it's working. All right, so now the first like integration method that we've been using was Euler step, and Euler step works. Like it's the textbook integration method for numerical methods. It's like if you know nothing else about integration with a computer, Euler step is like the one thing. It always works. Sometimes it doesn't work very well. So let's see what happens if we just say like Euler step this pendulum equation. Did anyone try this already? What happens? No? Or maybe. If we try to use like Euler steps to like go through every step of this pendulum equation. Not like this exact piece of code, but did you try Euler? Did you try to get Euler method to converge to that cosine omega t? Maybe not. And so I'll walk through like a little bit of what I'm doing here. This first step of time, like t equals lin space, time is just an independent variable. I can define it for anything. Like it does not matter what I tell time to be, as long as the first step in time is my initial point in time, like that initial value that I have. So right now I know when t equals 0, that my state is pi over 6 and 0 radians per second. Oh, I deleted it. Then however big my time step is, like that the change in the time step has to be based on whatever time I defined. So that one, either I can define dt and then make a whole bunch of steps of dt from 0 to n times dt, or I can use lin space and split it up into 61 steps, and now every step is a tenth of a second. So either way, but somehow t and dt, that's for you to decide as long as they make sense. I can't have a time step of 0.001, but time goes from 0 to 6 with 60 steps. It's like, then I only get part of the way there. Then this first step, again, is called initializing my array. In old school languages like Fortran and C++, you couldn't have an array unless you initialized it. Now it's good practice to initialize it. The just-in-time compiler for Python has gotten really good. So some people skip this step and always use the command .append. And it works, but sometimes you get like an off by 1 shape. Like your state has 61 steps, but your time has 60 steps, like sometimes, not all the time, or maybe 60 and 61. So I like to initialize it, but append has gotten much faster. There's less of a difference between the. Oh, whoops! I don't need this state lax. That one's also initializing an array, but initializing one that I'm not using. Then that first step at time 0, I don't want to solve for it because I already know it. So that's going to be my starting point where I'm moving on. So 30 degrees, 0 radians per second, and then step through. Let's get rid of that. For every other step in time, so not step 0, but step 1 through the length of time, I'm going to say that that state is whatever the previous state was with one Euler step. So the solution should look like a cosine, right? Like if I take a pendulum and I release it at 30 degrees, it should swing to negative 30 and then back to 30. Does that sound right? And yeah, pendulum kind of swinging. Does this look like a normal pendulum? I know it's in radians, but if we want, we can multiply by 180. Oh. What's happening here? Starts at 30 degrees, swings back up to maybe 90 degrees, down to 180 degree, negative 180, and then back up, starts like spinning around in circles. What happened? Yeah, what happened?
Does it like add up or like perhaps it's not a one to two? Doesn't it like if you have like two legs,
If it was like a double pendulum?
yeah.
Yeah, but then there would have to be. So one thought might be like maybe there's other physics involved in the problem, like a double pendulum or other things moving, but then this, like it would have to be captured inside my like equation of motion, right? Like somehow if it was a if I was allowing for double pendulum motion, then maybe there's two angles or maybe something, but something else would have to change. Like right now, it feels simple, right? Like when I gave it a 0, I got a 0. When I gave it a pi over 2, I got a negative 9.8. It seems like it's giving me the right acceleration for the right spot. So I don't think there's like an extra term in there. That would be like if my Euler step was also like a ChatGPT step. ChatGPT, take a step for me. It's like, did you mean double pendulum? And then, yeah. Sorry.
Isn't it like as time like goes on because you're using Eulers, the error also starts increasing?
Yeah, the error keeps increasing, right?
Yeah.
Yeah.
So like it might be after your first expected one.
Okay.
And then the error is going to increase. That's what the unexpected.
Yeah. So there's definitely like that, because we're integrating with the numerical method, we're introducing error. And you're right, like the longer you integrate, the more error kind of piles up along that time. Yeah, so we are starting to like pile up error that way. And yeah, that's like the main thing here. So So with numerical methods, it's kind of like, all right, if I want to solve for 6 seconds, then the question is how many time steps do I need to take so that I'm not accumulating a noticeable amount of error, or like something, some kind of value that I'm saying like, this is my threshold. I don't want that much error. And if it's less than 10 to the negative 16, then it's kind of, you're just chasing windmills or waterfalls. Don't go chasing waterfalls. So if 61 was too big, like 10th of a step, maybe 100th of a second is better, like 601. And now it looks better. It still looks like amplitude is increasing. So I have like, I don't have conservation of energy, even though my equation of motion is very much energy is conserved kind of solution. So I could go back up and say, all right, well, 601, maybe 1,000th of a second. And now it looks better. So Euler method, it'll always work, but sometimes you need a lot of time steps to get it to the solution that will work. So even this like couple of plots, this is called like a convergence analysis. I know it should be a cosine wave, and if I get time steps small enough, sooner or later I get cosine wave. But Euler step's not the only integration method. There's also like Hune step. With Hune step, it's called an implicit method rather than explicit. Explicit methods, they march ahead no matter what. Like they have a formula, they take the slope, they multiply by dt and move on. Sometimes they use multiple values of slope, like different Runge-Kutta methods. They might even have like 4 intermediate time steps that they're using. This one has this iterative correction that creates the implicit method, so the implicit solution. It will not move on to time step 1 until time step, or sorry, it won't move on to time step 2 until time step 1 has reached some convergence criteria. So in this case, I have like the next state. I keep updating it until the old next state matches the new next state. It's not like a really complicated thing, but it just keeps plugging in state and the right-hand side of the current state and the next state, taking the average slope between the two, and keep doing that until we hit some kind of tolerance. So it should be better, right? Because we're doing all that extra work. We added this big iterative correction to make this implicit method. Rather, we took the explicit Euler method, turned it into an implicit Hune step. And now using the same like 61 time steps that I started with, sure enough, that Hune step gives me a cosine wave that I expected in that first try. I don't have to keep trying to converge further. And I could probably even use less time steps. And I'm still like maintaining at least, maybe I'm losing some precision because I don't have as many time steps, but the accuracy is good because I'm matching a cosine wave pretty well. That was the question that nobody asked, but you got the answer. An answer. Yeah.
Can you go through when you're calculating the error, the convergence, you're showing those slope of either 1 or slope of 2 on a log plot?
Oh,
And
yeah,
can you
yeah.
explain the steps preceding that, where you're using, basically creating an array of DT values, then you're calculating the error from there?
Mm-hmm.
Can you explain just to begin with, the enumerate function?
Oh, enumerate is awesome. That's a great little. Let's give myself some space. So let's say I have like let's make it something interesting. Like I don't buy coffee anymore, but let's say we need sugar. We need what do I need? Flour, bread flour. Kohlrabi, and some cherries aren't really in season anymore, but coming up soon are the pomegranate, so we'll get some of those too. If I could spell pomegranate, I don't know if that's right. So in Python, the nice part, you can, anything that is like a list or a dictionary, you can like make a for loop to run through it. But sometimes you also need like the actual number of like, was sugar, here I can kind of tell because sugar is the first on the list, so I would expect shopping list 0 to be sugar. But sometimes I also need that to index other stuff. Like item amounts. So let's say I need like 1 pound of sugar. I need 1 pound. Let's be serious. We need like 2 pounds of bread flour, right? 2 kohlrabis and then one pomegranate. I really don't think I'm spelling that right. But like if I want to print out the amount and the shopping list item, then I need to be able to both use that shopping list item and index the thing in item amount. So I can say for I, comma, item in enumerate, now I can, I'll print out I and item amounts bracket I, so we get everything. So I get the index, and I can use the index to start indexing other stuff that has the same number of things, and then also whatever I was doing the loop through. So enumerate is a nice way, because like the old way is just you're always doing a loop with an integer, like changing that integer from 0 to something or 1 to something else. But the Python way is like you can use enumerate to get the values you want and indices if you need them.
How is this different than typical just for statement? Because obviously before you added the item amounts, could you still use the enumerate function?
Yeah. Yeah, like I could have just used enumerate and ignored the I. N values. I want to like plug in whatever values of n I want, just making, it's not a random list, but it's a list of things that I think are important. So I think 500, 1,000, 5,000 might be important. Maybe I also want like 10,000. Like I can add whatever numbers I want into that n values.
Because usually if we're doing a, for something in range, it's gonna be integer steps, right?
Yeah.
0 to whatever the.
Yeah, and predefined integer
So
steps.
enumerate allows you to step through the values in an array basically, instead of taking integer steps.
Yeah. Yep.
Okay.
Yeah. Yeah, and you still have that, but you still have an integer, like a 0 through length of that array. Integer,
in
value.
the instance of the example you had given, where it's for j, dt, in enumerate dt values.
Yeah.
So that means you're stepping through each dt value.
Yeah,
And
exactly.
there's 4 of them, so you're going to do that 4 times, basically in that loop.
Yep. Yeah, I think that one's in this part.
Yeah, it's in numbers. Get oscillations, yeah.
So there's showing that over approximation. And we want to look at convergence. So like in here, j dt for dt values. So I want to define dt values for these 4 different time steps. And here I can add other ones, like if I want to look at other stuff.
What's the point of using the np.empty like versus just np.zeros?
That one doesn't really matter.
Because you're just initializing an array, right?
Yeah. I don't know if there's a difference between the two. I mean, there's a difference in the result, but I mean, it looks like empty is a little quicker. So I don't know. Take it with a grain of salt.
And then in that same nested for loop, the very last line you do dot copy.
Yep.
What does that function do?
Oh, copies can get a little tricky. So if I say like x equals y equals this array of 1, 2, 3. So x is 1, 2, 3, y is 1, 2, 3, but they are literally the same 1, 2, 3 vector. So if I say, oh, I'm going to run it out of order, but y of 1 is now 10. Y is now 1, 10, 3, and x is 1, 10, 3, even though I never said x of 1 is 10. So if you don't want that, sometimes you want that to happen. A lot of times it's confusing when it does happen. So instead, rather than saying like x is this array, you can say like, I don't know if this will work if they're both. Yeah, because I'm still saying equal, equal, but so x is that. So now when I say y of 1 is 10, x is still 1, 2, 3, but y is 1, 10, 3. So it gets the result where I'm only editing y and not x because I made a copy. I'm forcing it to make a copy. So sometimes you do want that copy. In this case, I did want that because I keep saying numsol is something, like I keep overwriting it. So I'm making that copy to make sure that as numsol time j moved on to from 1 to 2, it's not also overwriting the work that I did from 1.
Gotcha. And then next, define get error function. Can you explain the index in numsol? Where you go from -1, 0.
This one is really, so the question was if you're online, I'm just trying to keep track of everything. This one is trying to grab column 0, but the last row. So the last row of column 0 is giving me the final displacement, like the last state 0 in this solution. And in that case, it's going to be my whatever final time I had in my solution, so like capital T plugged into this cosine omega times t.
Gotcha, because we're stepping through dt's to get eventually to the full capital T period.
Yeah.
So our numerical solution, the final one, will be equal to the analytical one at time capital T.
Yeah. Okay. And there's more than one way to calculate an error, and I can't remember if I was talking about that on Friday here or the next section, but like I could, when we look at these two plots, as it's coming up, I can see that the dashed numerical line is different from that orange, the analytical line. So there is a difference between them, which means there's an error. One way to calculate that is, like, you can find the average error over all time, like sum up every difference, and but then you still end up with one value. Another way is just take the point at the last step, which you expect to be the highest error, and then use that. And that's what we're doing here. Let's just take that last step and compare it to what we think we know, what we want it to be.
And then can you explain the last where you're plotting the log-log plot?
Yeah.
Can you explain how the log-log function works, and then also why you're doing 10 times dt values?
Oh, 10 times that?
Yeah.
Let me make sure that I have. So I'm going to run through these, make sure that it's ready to rock. Okay. So when we're taking log-log, like really I could take both of these and plot them, and then take np.log of 10 of both of the values. So when you're doing like a log-log plot, default is that your x and y axes are now on base 10 log scale, where every major point is like a 10 to the negative, or 10 to the something, 10 to the power of something. So I could kind of build my own with regular linear plots, but take the log of all my inputs. But log-log is a nice like shortcut for that.
So it takes the log of the x and y inputs.
Yeah, for log-log, it takes both axes and turns them into log base 10 scales. And then the reason to put a 10 here, it could be any number we want. It's just changing the offset of what this straight line is. So if I plot a value versus itself on a log scale, it's a slope of 1. Even on a linear scale, it's slope of 1. And here, if I just say dt versus dt, it's offset by 10 to the negative, like in 1 order of magnitude. So it's hard to see how close the slope is. So multiplying by 10 just changes, like, all right, on a log scale, bring it up by a factor of 10. So I could say 11 if I wanted to get it like even closer.
Because you're just trying to compare the slope.
Yeah, so it's just giving me a reference point of like, is this slope 1 or is this a slope 2? Because if I do dt squared on a log plot, now it doubles the slope on a log plot. I'm saying on one axis it's dt, but on the other axis it's like the square of dt. So a parabola, if you put it on a log plot, looks like a straight line. Same for most polynomials, they look like straight lines. Yeah. So the real reason for that 10 is just, yeah, just to get it in the spot that I wanted it. Maybe even like 15 if I want it to be too high. 14. That's pretty close. 13, Halloween. Halloween's coming up. Good luck. If that's not linear convergence, I don't know what it is. That's slope of 1 on that log scale. Definitely. Cool, thanks.
So when you're doing the log function, so np.log, that's based on, or is that based on?
Default for log is basically
Okay, so when you're doing a log, when you're converting to the log scale, what is the actual mathematical function that's going on? Because it's converting your inputs, right? So it's changing the numerical value of those inputs to elsewhere, right?
I mean, kind of.
It's keeping the array the same, like those values are never going to change.
Yeah.
But when it comes to plotting, it's doing some function to change the value to put up the scale, right?
Kind of. It's taking the plot that you're making and putting it.
So it's just changing the axes, basically.
Changing the axes.
These values are going to stay the same.
Yeah, but the values are still the same values. Yeah.
Okay, so it's only changing, the axis was going to go from 0 to 10. It's now going to be from, with steps of 1, 2, 3, 4, 5, 6. If you're just going to plot normally. Instead, now it's going to go 10 to the minus 1, 10 to the minus 2, 10 to the minus 3.
Yeah. Yeah. Yeah, it's an actual plotting command more so than like data processing.
Yeah. So it doesn't change the x or y.
Yeah.
If you did it where you did np.log within
there you were like reprocessing to get it into a linear scale.
Okay.
Yeah, like if you were drawing it out by hand in the old school way, beforehand you choose like, all right, am I gonna have linear scale or log scale?
Yeah. Got it.
Yeah. Then there you might pre-process to make it easier.
Yeah, that makes sense. Then it looks weird. You just plot it normally.
Oh, if you just
take the log scale out.
Yeah.
So that wasn't the dt values on the log scale. Still.
That one is the same. That one ended up being the same because it just happens to be
the right spot.
Yeah, because it's always, if it starts at 0, you They have a slope of 1. There's a lot, yeah, there's a lot of symmetry in that one.
So if you plot something on a log-log scale, it has a slope of 1, but it still has a slope of 1 not on a log-log scale.
Not always, because it could be like 5 times x. That the slope on a linear scale is 5, and on a log scale it's going to look like a slope of 1.
What's that?
Let's grab. It's not going to like the 0. Sorry, give me a second. So like both of these are like 2x and 3x, so 2 different slopes on a linear scale. But when I put them onto when I take the log of that, the log of 2x versus the log of 3x, like they're both increasing at the same rate, like in powers of like if I multiply 1 by 10,
the power of the independent variable, basically.
Yeah. So how fast is like 2x versus 3x increasing, like in powers of 10?
Is there still technically a difference in that slope on the log-log plot?
No, no
Or
difference.
Just so small you can't see it? Or no?
Nope, no difference at all.
So as long as the power of x is the same, you're going to show the same slope on the log-log plot.
Yeah, exactly.
Or if it was, 2x versus 2x squared, you're going to see a slope of 1 versus 2.
Yeah, because when I take can't spell log of 2x. If I multiply, I think this is the same as like log of 2 times log. Is that right? Or no, it's adding. Sorry. So on a log scale, by changing the linear slope, making it like 2x, 10x, 5x, it's changing how much it offsets. Like it's going to have a different intercept, but it's not changing the slope because it's still log of x. It's versus like log of 2x squared and log of 3x squared is log of 2.
Pull the exponent out in front, right?
Yeah.
The actual mathematical operation for log is 10 to the y equals 2x in this case.
Yeah. Yeah, so we're just fun like exploration of what is a log scale. But yeah, so it's just giving you that highest polynomial order term. Because I don't even think like on a linear scale, 2x plus x squared versus x plus x squared over 3, I think they're both going to have the same yeah, I guess there is like a little bit of a difference. I mean, there's no difference in the curves, but now it's like kind of a curve instead of just a straight line. But still, they're both offset by the same amount because they're both a 2 times x and then a 1 times 2 times log x and 1 times log x.
Yep.
Yep.
Thank you.
Yeah. Oh, time flies when you're on a log scale. All right. Yeah. Now we're at 10 to the 1 hours. Time to go. Went from 10 to the 0 to 10 to the 1 in like 1 minute. Thanks for joining.